What is going on, guys, and welcome back to another one of the videos. Today we're going to be looking at another quadratic equation, so let's head right into it. I figured out, by the way, how my pens work. I did not know before, but this works the same how a normal pen works. So like you have to press this top down, and then I don't know, but anyways, my black pen is working again, so we can actually write in black. That is great. Now the contrast is going to be insane. Okay, so let's just have a look, right? So, but today is a little bit different because, as you can see in the title of this video, there's question marks there. It's not just a quadratic equation, it is also something new, a new concept of mathematics. I mean, it's not that new, but for this channel it is new, so let's just have a look, right? So we need a quadratic equation where b squared is smaller than 4ac. Okay. Let's just have a look, right? Let's just do it like this, right? So let's choose for a and c big numbers. So let's say our y of x graph is equal to 2x squared plus, let's say, I don't know, 4x plus 25. All right. So this is just some random graph, right? I don't know what this graph looks like, but that is just not the question at the moment. The only question that really is here is what happens when we try to solve for x12, right? So let's actually go ahead and do that. Let's write down the formula, right? We have minus b plus minus square root of b squared, sorry about that, b squared minus 4ac all over 2a, right? Let's just go through this fairly quickly, right? ax squared plus bx plus c, right? And what condition has to be true that this formula even applies, right? And of course the condition for this to be true is we're searching for the points of intersection of the graph with our x-axis, right? So that means y of x has to be 0. Right? And then this is true. Okay? So let's just do this really quickly. First, we divide by a, isolate the x squared plus b over a times x plus c over a is equal to 0. The question is, maybe why do we do this, right? We do this because if we can say where this comes from, right? If we can do this ourselves, this whole factorization and all that, we can relate to way better why this formula even exists, right? So now let's continue on. We have x squared to this. Now we need to complete the square again. So how do we do that? We need x squared plus b over a times x plus some term is equal to minus c over a plus some term. Now how did we do this last time? We looked at what term. Well, basically, how does this term happen, right? Like, how does this term even get there, right? So this is basically plus plus. So we have a plus b squared in the brackets, right? And we have a squared plus 2ab plus b squared. So this is 2ab, right? This is our 2ab, and this is our b squared term. So we need to put the a away for our minds. So we just say, okay, b over a times x. We can cancel out the x because this is our b term and this is our other term, right? But this is definitely our b term. And we have 2ab, so we need to divide this whole thing by 2 to get to our b, right? So b over 2a is our desired answer. But the problem is that it's b squared. So our b is not b over 2a, but our b squared is of course b over 2a to the power of 2. So we have b squared over 4a squared plus, and of course we have to do that on the other side as well. So just to make that legitimate, let's just write that here. And we have b squared over 4a squared. Now what we do, maybe let's do this a little bit faster because I've already done this. We have x plus, factor this out, b over 2a squared. This is just the same term here, right? And then we have is equals to, maybe we can the denominator, we can put that on 1 right away. So we have 4a squared, b squared minus 4ac. We take the square root, we say x plus b over 2a is equal to plus minus the square root b squared minus 4ac over 2a, and then we just plop it over, minus b over 2a, same denominator, great. X is equal to minus b plus minus square root b squared minus 4ac, and all over 2a. Good, great. Let's just keep this, let's just get rid of this because it's just a quick revision for us. Now that we have successfully completed that, let's just go back to our normal equation, right? So, plugging in the numbers, right? Let's do this maybe a little bit slower. A is 2, B is 4, and C is 25. Right? Good. Let's plug that shit in. Sorry about that. Good. So we have, plugging the numbers in, B is equal to 4. So we have minus 4 plus or minus square root of B squared, which is just 4 squared, which is just 16, right? Minus 4 times A, which is just 2, times 25. So we have 2 times 25, which is 50. Minus 4 times 50, all over 2A, which is just 2 times 2, which is just 4. Great. Now, let's just pull it. Let's just put it here. And we continue. X12 is equal to, right? Let's go minus 4 plus minus square root of 16 minus 200, okay, over 4. And then we have minus 4 plus minus square root of minus 184 all over 4, right? And this is actually where today's topic comes into play, right? If we maybe say, okay, we have two x's, right? X1 is equal to minus 4 over 4, which is just minus 1, plus square root of 184 over 4, and x2 is the same as minus 1 minus square root of 184 over 4. Now the important thing here to notice is that we have a negative sign in the square root. So what does this mean? How does this how can we interpret this, right? What is this even saying? Well, when we have a negative sign in the square root, that means that we're taking the square root of a negative number, right? So basically what that means is we have square root of negative number. So let's just say negative 5, right? And this is an important concept in math. Square root of negative 5 has been defined by mathematicians by 5 times I. This equals this. And now you might say, okay, how is this even possible? Because taking the square root of a negative number, right? Is that even fair? Can we even do that? Not really, right? Because at what number times what number, or what number times itself can even equal a negative number, right? Because we're basically looking for this, right? We're basically looking for x times x is equal to minus x, right? Minus x squared. That is just not the case, right? We do not have any number that applies here, right? So mathematicians invented something. Now one step that I skipped here is, instead of doing this straight away, which is of course true here, let's just take it a step back. Let's just write square root of negative 5 is equal to, how can we factor this? Negative 5, right? So you guys know that multiplying and dividing by 1 doesn't change the value, right? And that's exactly what we're going to do here. So we're going to say that 5 times negative 1. Oh, sorry about that. This is of course square root of 5, right? So good. Anyways, back to this. So we have square root of negative 5, which is just the square root of 5 times negative 1, right? You guys can relate to that, right? That is basically just factorization. Good. And now we can see that I must be equal to the square root of negative 1, right? So by the properties of square roots, I can take the square root out and take the square root of both of these factors, right? So we can say 5 times square root of negative 1. Okay? And as you guys can see, in the end, as we've just proven here, I must be the same as negative 1. Right? I must be the same as the square root of negative 1. Good. So now that we have established that, we can see that we can now take square root of the square root of negative numbers. Although it does not intuitively make sense, because what does that even mean for our number, right? I'll plug in the values for this. We get our two answers, right? Which is just one. One answer is -1 plus whatever, and one answer is -1 minus whatever. What does this mean, right? If I were to now draw this graph, my pen, then yeah, let's just maybe do that up here, right? So let's just say we have a system of coordinates, right? And we say we have our x and y axes. All right, now how are we going to draw this, right? Well, I'm not even going to do this up to scale, but you guys are going to tell me now, how do I draw this? Great, so you guys got it. So actually, if I want to draw this, I don't even need to, I mean, of course this is not to scale, so theoretically it's not the same thing, right? But what I have to consider is when I have these two terms, what I absolutely have to consider is that I do this, right? Let's just do this approximately. So we've learned that 2x squared means that it's got to be a little bit steeper, right? Than the normal one, than our base parabola. We learned that +4 means that it's actually shifted to the left, and +25 means that it intersects the y-axis at 25, right? So it's 25 here, and yeah, I don't know. Let's just maybe draw it like this, right? Yeah, that's maybe a little bit too, but it doesn't really matter, right? Let's just say that this is our y of x, right? Y of x. Good. Now, one thing that is really important to keep in mind here, guys. As you can see, we have no intersections with the x-axis, right? Not even going to infinity, and that is the exact point of this I. What this result has given us is something that this parabola intersects the x-axis at some imaginary point. And this is actually what today's topic is about, is imaginary numbers. Good. So let's just maybe keep these two results here, right? And let's just maybe get rid of all of this. Let me actually write down the topic. So we have got imaginary numbers, right? And one important thing to know is that imaginary numbers, it's not really imaginary numbers, because I think when we talk about something, it's important to know where to apply these numbers, right? So we have imaginary numbers, and we have applications. So we have this, computer science, and others. Great. So now that we've established what actually where we can apply these, right? I'm not gonna get into detail here because I'm not any of this, right? I'm not an electrician. I'm not a computer scientist. I'm not a quantum physicist. So let's just, yeah, maybe talk about what they represent, right? So imaginary numbers is actually, when we think of imaginary numbers, we think of I, right? And one important thing maybe to say at this point is that when we talk about computer science, it is /J, right? These two are the same. They just have, the computer scientists usually say J, and we mechanical engineers usually say I. But it's the same thing, right? Both are equal to the negative square root of 1, right? Good. This is not a division sign, right? I'm just going to write over here. Good. Great. Now let's actually have a look at what is happening and how we can maybe approach this, right? So let's actually do it in a way in which we look back at our, I don't know what it's called. I think primary school, right? So in primary school, you guys learned that you have, your numbers. You have 0, and 0 is this kind of not positive, not negative, neutral number. It doesn't really matter, right? I mean, it does matter in the mathematical sense, but not right now for explaining this. So we have 1, 2, 3, 4, 5, 6, and so on. We have -1, -2, -3, -4, -5, and so on, right? All the way to infinity. Negative infinity, of course, here. Great. And now, Mr. Gauss was actually the dude who invented not this, but what I'm gonna draw, right? So he just thought, or the basic idea of imaginary numbers is that we're not just thinking in this one-dimensional like line space, right? Because it's just a one dimension, right? You're only going left or right. You're not going up or down. You're not going forward or backward, 3 dimensions, yeah? You're only going left or right. So Gauss thought, why don't I make numbers 2-dimensional? Alright guys, so a shower later. No, because the camera has to cool down a little bit. Maybe get like that. Alright, so the camera had to cool down, but and I moved the scenery a little bit. So yeah, let's have a look. What do these results actually tell us? So we have a plane here, right? And we said that instead of just having real numbers, right, such as 1, 2, 3, or fractions, right, or irrational numbers, which are all real numbers, right, we have imaginary numbers. But as I said, these numbers are being called imaginary, but they're not actually imaginary. They have been discovered rather than invented because of the various very important applications where they are being used, right? So we have to differentiate between an invention and something that was discovered. Okay, that just on a side note. Now let's have a look. So why did I draw these two kind of lines, right? Good. So we have one part of this thing is what we call imaginary, and one part of this expression is what we call real. And those are exactly our two lines, right? So one line is real, and the other is imaginary. And we usually do it like this, right? Or you can also do a little I. Doesn't really matter. It's sure. I mean, language not that important. Math's important. Good. So you have the imaginary part is here on this axis, and you have the real part which is just here on this axis, right? And now the question becomes, what does this and this do? Well, when we are in this plane, right, and this is actually Mr. Gauss has invented this, so I'm gonna write this up here, right? We have Mr. Gauss with double S, and so what we call this, to honor this guy, is we call this Gauss's number plane. And so we call this Gauss's number plane for a reason, right? He invented this, but what does this actually display? Why do we call it that? Well, now instead of thinking one-dimensionally about numbers, he thought two-dimensionally about numbers. A plane, right? Two ways to move. Up, down, left, right. Instead of only moving left or right. So you guys have to think back, right? This line right here, or this axis, only represents the real numbers, right? So you have 1, 2, 1/2, -5, and all that, right? But then you also have another axis, which is the imaginary numbers, right? And this is where this imaginary thing, now I learned that I need to press this before I actually use these pens, so that I actually get a, there we go, look at that color, holy crap. We have these two imaginary parts, right? Of course I should, let me just correct that maybe. Should also take in the positive or negative part, right? So you have the imaginary part. And then So you now have two different parts on the plane, right? You have an imaginary part and a real part. How do we sketch this? Well, we sketch it in a way in which we normally sketch it, right? This is basically like having two coordinates, right, on this plane. So let's just maybe show the result before we do anything. So actually I had to go because got a haircut, but that don't really matter. We're back at it. 1 unit is equal to 3 centimeters, and yeah, so maybe let's just have a look, right? So, well, of course these are 1 centimeter long, but it's 0.3 periodic units. Anyways, let's maybe display the result. So we have two results, right? 1 and 2. So let's just maybe do this. So we have -1, and actually the way that you do this is the way in which you normally would, right? So you have -1 is here, real axis, and then you have, that's why I drew this, because it's 3.39, so it's about right here, and the interception point is our point, right? Not exactly, it should be a little bit lower, but you guys get the point, right? So we have the same here, so we have 3, and we have -1. Just go straight up, and the point is somewhere here. Now, one important thing to know is that what actually is our result in this number plane is connecting always from the 0 point, right, from 0, 0 to our point of the result. So we have -1 plus 3.39i, that is this one, and we have -1 minus 3.39i, that is this one. But the result is actually this arrow, right? So this is a way of displaying imaginary numbers, right? So basically there is some things to know about this, right? One thing to know is that when we have an imaginary number, the usual way of writing this is this: a plus bi. So you have the real term, right? So you have this one, re, and you have the imaginary term, which is some number multiplied by the number I. And that is the exact same thing which we have here, a plus bi, right? A plus bi. Of course, they can be negative, right? So this is the way that you usually write imaginary numbers. And this is one way of displaying imaginary numbers. Now, what I have not explained yet is why we draw it like this. The idea behind this is that instead of having only one-dimensional numbers, it's having two-dimensional numbers. Basically, having coordinates for a certain number, right? So, in this instance, you have a point here and a point here. That is the coordinates of this number, which consists of a real and an imaginary part, right? And so, but the real thing, when you think about imaginaries, is really flipping the numbers by 90 degrees, right? So basically, think about it this way. You have a number, and you multiply, and you have a number, you have x, right? And you have a number x. It's somewhere here, a normal number, right? And then you multiply this number by square root of -1, okay? Then you just turn it by 90 degrees, okay? So maybe let's do a little bit of a table here, right? So you have, let's assume x is positive, okay? So we have positive, okay? So we're going in this direction, right? Any number. Then we say, step 1. Then we say step 2 is x times square root of -1, aka times I. Then we turn this number by 90 degrees, and it's actually pointing up now, right? So you have x times -1, which becomes imaginary, right? And then, if you do this again, you multiply again by the -1, right? But then, square root of -1 times square root of -1 just equals -1, right? Because it's the square root. So you get -x, and which is negative. And that actually makes sense, because when we multiply by -1, we're rotating not only again by 90 degrees, but we also should be going in the other direction, so that actually makes sense, right? And then by 4, we have another rotation of 90 degrees. Negative x times square root of -1 is, again, imaginary. This time into the negative, right? Because we're going down and not up, imaginary positive. And then, the way that we get from 4 to 1 again is again by multiplying by -1. And then we have -x times square root 1 negative 1 times square root negative 1, which is just minus x times minus 1, which is just the same as x. So it's a positive number again. So this is basically a cycle with which we do these calculations, right? And this is the basic idea of these imaginary numbers. You have an imaginary part and you have a real part, right? This is the way that we display it in a system of coordinates, right? We just draw an arrow. It's always an arrow. It's usually, it looks like a vector, but it's not really a vector, right? And then there's also some other things. Now you guys might realize that you can actually display the length of this vector. Let's just call it 1 and 2, right? You can actually display the length of 1. So let's just write length of 1 is equal to right angle triangle, right? Again, you have here and you have this. So you actually just take square root of the real part plus the imaginary part without the I, right? I'm just going to put that here without I. And that is the way that you actually get the length of this, right? The length here is the same. Maybe one thing that we also need to think about is whenever we solve these equations, those quadratic equations, right? We always get these arrows which are mirrored on the x-axis, right? Because you always have a plus and a minus, so that means that any way that this first vector is gonna be pointing, you're always gonna have the exact opposite and the exact length mirrored downwards, right? That's gonna be our negative vector. Good. What else is there to say? Well, you can also define these vectors by only giving this angle here and the length of the vector, right? So you can. This is actually called the phase angle. So phase angle. Phi is the phase angle. So you could just say, okay, the angle is this and the length is this, and then you could draw this in a way in which we just did now, right? Good. Thank you so much for watching. I'll see you in the next one, guys. Maybe think about this because this is a very important concept in mathematics. I will do some practice with this, and we'll also do some practice with the forces and torques, which has already been recorded, but it doesn't matter. It's not done yet. But yeah, I hope this was a little bit helpful, and we're maybe going to look at some examples and do some practice. Thank you guys, and have a good one.